Okay, so now in this second part, we'll keep doing examples. And so we're on example 3, I believe. Let's try the integral of 1 plus e to the x minus 1 over x squared dx. So we want to find the function whose derivative is 1 plus e to the x minus 1 over x squared. So as before, we have a sum of terms. So the sum rule tells us that we can split the antiderivative into a sum of antiderivatives. The first one will be the antiderivative of 1 dx plus the antiderivative of e to the x dx. And then the difference rule tells us that we can, the last term will be minus the antiderivative 1 over x squared dx. So it works very much like differentiation. We sort of split our problem into the sum and difference of simpler problems. Okay. Now, the antiderivative of a constant is just going to be, the constant 1 is just going to be 1 times x plus a constant, which I'll just have all the constants of integration for each of the 3 parts, just I'll put them into one constant. So the antiderivative of 1 dx will be 1x. And we learned that the antiderivative of the exponential function is just going to be the exponential. And now this last one is a little trickier. The easiest thing to do is to rewrite 1 over x squared as x to the power. And 1 over x squared, we can think of this as x to the 0 over x squared. So if you were to simplify the exponents using the exponent rules, you would find that this is x to the negative 2. And there's a constant of integration there, which we haven't finished finding the antiderivatives, so I'll just keep the constant of integration in there, so to speak. Okay, so we have x plus e to the x minus, and now we need to use the power rule. The power rule for finding antiderivatives say we have to keep the base the same, increase the exponent by 1. So instead of negative 2 plus 1 will be negative 1. And then to compensate, we should divide by the new exponent. And then we'll get a constant of integration. And we can simplify that to get x plus e to the x plus x to the negative 1 plus a constant of integration. And we can check that is in fact the antiderivative of 1 plus e to the x minus 1 over x squared by taking this expression and differentiating it with respect to x. So d dx is x plus e to the x plus x to the negative 1 plus c is just going to be 1 plus e to the x minus x to the negative 2 plus 0. And that is the same as the integrand that we started with. So we have correctly found the antiderivative. So let's do one more example. Now let's find the antiderivative of x to the 4th minus 1 over x squared. And we're integrating with respect to x. So this is a trickier problem, if only because the way the problem is written down is not how you're actually supposed to go about doing it. So we have a fraction with variables on the top and bottom. Usually those are pretty complicated, unless you can first apply algebra to simplify the problem that you're being asked. So that's what we're going to do in this case. We're going to first apply algebra to simplify the integrand. And algebra tells us that we can split this apart and do x to the fourth over x squared minus 1 over x squared. And the first term will simplify down to x squared, and the second term will be minus x to the negative 2. And you might notice that I have not put parentheses often when I put integrals. It's a matter of taste. If you're more comfortable putting parentheses in here, to remember that you're integrating the whole thing, x squared minus x to the negative 2. If you're more comfortable with that, go ahead and do it. But you don't really have to, because the integrand is everything between the integral symbol and the dx, or the differential of whatever variable you're using. Okay. So, just as before, we have a sum or difference of things. In this case, we have a difference. And we can simplify our problem by breaking this problem up into smaller parts. So the difference rule tells us that this will be the integral of x squared dx minus the integral of x to the negative 2 dx. And now each of the problems, each of the parts here, we can solve just using the power rule. And the antiderivative of x squared will be something times x cubed, some number times x cubed, and we need to have a 1 over the new exponent, so that when we differentiate with respect to x, we bring down the 3, cancels with the coefficient, we keep the base the same, reduce the exponent by 1, and we end up with x squared. And now we apply the power rule for finding the antiderivative of x to the negative second. So again, we keep the base the same, increase the exponent by 1, and negative 2 plus 1 is negative 1. And then we have to divide by the new exponent, so that when we apply the power rule for differentiation, we bring down the exponent, which cancels with this term right here. We end up getting a 1 for a coefficient. Then we keep the base the same, reduce the exponent by 1, and we end up with just x to the negative 2. And then finally we have just the constant of integration. And I think it's a great idea when you first start doing antiderivatives to always check your answer by differentiating. And then, because it's easy to sort of get the two directions confused. The rules are very similar, and it's easy to get them confused. But we learn differentiation first, and that's maybe a little easier. And so we can always check that we did the problem correctly by differentiating the answer we got and making sure that we get something which is the same as the integrand. So in this case, derivative with respect to x, 1/3 x cubed. This will cancel to just be plus 1, so we get plus x to the negative 1 plus c. The derivative of that will be 1/3 times 3 times x squared plus negative 1 times x to the negative 2 from the power rule for differentiation plus 0. And 1/3 and 3 cancel, so that we end up getting just x squared minus x to the negative 2 plus 0, which is just x squared minus x to the negative 2nd. So that's exactly what we started with. So we've done the problem correctly. Okay. So that the rules we've learned so far will let us do lots of different integrals, lots of different antiderivatives. We have an analog for the sum rule, the constant multiple rule, the power rule, even the rule for differentiating exponentials. One thing we don't have quite yet is the product rule, which will come later, or an analog of the product rule, and also an analog of the chain rule, or the general power rule. We called that a special, or we gave that name to a special case of the chain rule. All right, so in the next section, in section 6.2, we're going to learn about integration by substitution. And the idea here is basically we want to undo the chain rule. And we're going to undo the chain rule in a special way. We're going to undo the chain rule by making a change of variable. So what that means is we're going to start off with an integral, perhaps an integral with respect to x. And what we're going to do is we're going to change to a different variable whose meaning we choose, which makes the integral simpler. It sort of will expose the basic structure of the thing we're trying to integrate. And then with respect to this new variable, perhaps it's u, often we'll use the letter u, and many people call this technique u substitution. Then the new integral with respect to u will be easy to do, usually. And then we'll get a function of u, but we'll know what u was because we picked what it meant. And then we can use that to eventually solve the original problem. We get a function of x. It's more complicated, it's less complicated than it sounds, as long as you sort of believe that it works. So I want to start off with an example of where you might get the idea from this. So let's look at the integral of 2 times quantity 2x plus 4 raised to the 5th. We're integrating with respect to x.